Hi again, everyone. And now you can supposedly see my presentation as well. I'm Zoltán Lehóczky, and I would like to tell you about our research project Hastlayer and how you can use it to turn your .NET software into computer chips. So I think it's quite an interesting topic. Let's see what it's about. Just a bit of introduction before anything else. I'm from a company called Lombik. We are based in Budapest, Hungary, but actually all of our clients are foreign. Mostly from the US, but actually we do have UK clients as well. And our customers also include companies like Microsoft itself, Live Nation, or even the Smithsonian Institution. And day to day we are doing .NET-based web development, and we offer related services, mostly with an open source content management system called Orchard. So if you work with .NET on the web and you haven't heard of Orchard, I highly encourage you to check it out. There is also a .NET Core, ASP.NET Core version of it called Orchard Core. But when we are not doing Orchard-based web development, then we are working on some research and development projects like Hastlayer. So let's see what it's about. Just a word of warning, Hastlayer is pretty much in an alpha stage currently. So it works fairly well, it has some nice results, but it's not ready for production level workloads yet. Why this is the case, I will tell you a bit later. Alright, so what is Hastlayer to begin with? Well, Hastlayer is a tool that takes a computer program and creates an equivalent computer chip out of it. So we could say it creates an equivalent piece of logic hardware out of it. So basically it takes some logic which is expressed as software form and creates some equivalent logic which is expressed as hardware form. And all of this happens with some magical devices called FPGAs. Have any of you worked with FPGAs before? Please raise your hands. It seems one person and somebody else in the first row was a bit shaky. Yeah, so probably 1.5 persons. That's not a surprise because usually us software developers don't work with FPGAs. Because what are FPGAs? FPGAs, or field programmable gate arrays, are basically computer chips that can behave like any other computer chip, within limitations, of course. So they can be dynamically rewired on the fly to behave like another processor, for example. So if you want a computer vision processor, for example, you can configure an FPGA to behave like that. And now, if you Google something on Bing, let's say, then, for example, we have already used FPGAs. Because as of a few years ago, Bing is accelerated by FPGAs. FPGAs are also in Azure. They are not yet publicly available directly. But if you are using the machine learning kind of processor called Project Brainwave by Microsoft, then you are already using FPGAs as well, because those Brainwave processors are configured into Microsoft's Catapult FPGAs. But FPGAs are sometimes used in household appliances like routers, or if you went to a doctor and got an X-ray, PET scan, or MRI scan, those machines commonly have FPGAs as well. And self-driving cars are not without them either. However, you need to be a hardware engineer to utilize an FPGA, since it's basically logic hardware design. So to get back to our train of thought, what Hastlayer does is that it takes a computer program and creates an equivalent FPGA logic from it. And of course, we are on a .NET meetup, so not just any programs, but we are talking about .NET. And since Hastlayer processes the .NET assemblies, the common intermediate language assemblies, because of that, at least in theory, not just C#, but any other .NET compatible language can be used. And that includes, of course, Visual Basic, also C++, or even functional languages like F#, or even scripting languages like Python, PHP, and JavaScript can all be turned into FPGA logic. All right, but why are we doing this? to give you a bit of an idea, here's a totally non-scientific, very crude overview of the different merits of different computing devices. And this should give you an answer. Now, talking about parallelism, the chart on the left, so how many things can this device compute in parallel? For example, here CPUs, the chart in the blue, are on the lower end here, because a CPU has probably 4, 8, 32, 64 cores, but that's about it. GPUs in orange, however, are highly parallel devices, having even thousands of little processing cores all working in parallel. Now, FPGAs in gray are kind of a middle ground here, because FPGAs don't really have cores, but the level of parallelism you can get with an FPGA is in the order of magnitude of hundreds, sometimes thousands. Now, what you can run on these different devices, the complexity of programs, varies as well. As long as it's a piece of software, you can run it on a CPU. Sometimes with emulation, but that's about it. The CPUs win here. GPUs, the programming model is much more limited, so I would say they are on the other end here. FPGAs are again a middle ground here, because although you can't directly program an FPGA, but with a high-level tool like Hastlayer, you can still write a program that will be turned into some FPGA logic, and what you can do there is roughly in the middle. And lastly, let's talk about power efficiency. So how many computations can you do with 1 watt of power? And this is where FPGAs really shine, because FPGAs are basically application-specific processors. They just do what you need them to do. There are no noisy neighbors. There is no operating system to run. It just computes what you need them to do. And because of that, they can be very power efficient compared to CPUs and GPUs. But there is a huge downside, and as mentioned, the issue is that with FPGAs you have to be a hardware engineer. So to learn how to use an FPGA, it's a very high effort task. But with tools like Hastlayer, we want to bring this down onto the CPU programming level. So, in a nutshell, what we aim for with Hastlayer is to get all the computing benefits for all of us software developers. So, if your algorithm is highly parallelizable and is compute bound, then with FPGAs and with Hastlayer you can get a performance increase and substantial. And at the same time, you get higher power efficiency, but it's still software development as usual. And now let's have a demo on how to work with Hastlayer. So now we'll switch to Visual Studio, and what we have here is example algorithm. This is not something very useful, but it's kind of an exaggerated example of the class of algorithms that are especially suited to be accelerated by Hastlayer with FPGAs. And this is called a parallel algorithm. Surprise, it's a highly parallelized algorithm. And what it does is, well, first it takes an input number. And then it starts tasks. Now, I guess everybody is familiar with the task parallel library here and with tasks, but just to recap, when you start a task like this, then the .NET Task Scheduler will eventually take a thread from the .NET thread pool and execute the body of the task on that thread. And how many such threads can run in parallel depends on the platform your application is running on. Now, in my machine, I have an Intel i7 CPU with 4 physical cores and 8 logical cores. So the hardware level parallelism we'll get is, well, around 4. But we are actually starting 280 tasks here. Why 280? 280 because this many will fit on the FPGA that I have here. And probably my picture is too small for you to see, but I actually have an FPGA for this demonstration here that I'm showing to the camera. And because what will happen is that when Hastlayer will process this code and will create a hardware implementation out of it, these 280 tasks that we start here will be turned into 280 little processing cores, so to say. So on the hardware, we will get a hardware level parallelism of 280. And that's where the performance benefit of FPGAs comes from. Now, what we do in these tasks is pretty simple. There is a bit of conditional logic here, which is executed 10 million times. And then the result is returned back. Then we wait for all of these tasks to finish. And once that is done, we wait for the results and sum these results together, and this will be the output of the whole algorithm. So as you can see, just an example, but kind of an easy to understand one. Now I'm starting this little console application this is part of, and what happens now is that Hastlayer journeys the hardware implementation. We won't have time to look at that, but I will show you the link to this later where you can check it out. And once that is done, it will start to communicate with the FPGA and execute this algorithm 3 times, and finally 1 time on the CPU. Now, as you can see, all 3 times it took around 300 milliseconds. Actually, almost exactly the same amount of time, also because the FPGA is an application-specific processor. And it took 300 milliseconds on the FPGA, but on the CPU, it took around 3 seconds. So the CPU was about 10 times slower than the FPGA. Now, of course, this wasn't a very scientific measurement. My machine is doing a lot of other things, but still, this should give you a bit of an idea of what's possible with Hastlayer and with FPGAs. And this is just a small, slow, relatively cheap FPGA development board. But we are working on supporting bigger boards. So let's wrap up. This is the state of Hastlayer, but what we are working on is that we are bringing more use cases to Hastlayer. We are field testing it. For example, with our partners at the Wigner Research Center for Physics, which is part of the Hungarian Academy of Sciences. Some pretty smart guys there. Mostly physicists. We are also working, we are actually mostly done with floating point support, but not with standard floats, but with a new floating point number called POSIT, which was invented by a mathematician called Dr. John Gustafson, and POSITs are supposed to be even better than standard doubles and floats. We have a .NET library for that, that you can also check it out if you are into these things. We are also working on making Hastlayer high-performance computing ready by supporting bigger, faster, high-end FPGAs. And it seems that FPGAs are also coming into every data center out there, so that's a good news. AWS already offers FPGA virtual machines. As mentioned, Azure already has FPGAs, well, not yet publicly available. And Intel, as of about 2 years ago, I think, is an FPGA manufacturer as well, because Intel acquired Altera, the then second largest FPGA manufacturer. Well, now we can purchase Intel FPGAs. And what we hope for, and what they are actually not just planning to do, but are already in the process of rolling out, are CPUs built together with FPGAs, which will open up a whole new lot of possibilities. So, if you like this, and I really hope you did, go check out the SDK on GitHub. You can use Hastlayer for free. Be ready, because FPGAs are coming. I would say that with FPGAs, we are roughly where we were about 8 years ago with GPUs. It's still a playground of specialists, but eventually they become more mainstream and more accessible to all of us. For example, thanks to tools like Hastlayer, I would say. So that's it for this lightning talk. Thank you for your attention. If you'd like to check out Hastlayer, here are some URLs, and do get in touch with me if you have some good ideas for that or some questions. And now we also have probably time for one question.
Well, what do you support? What FPGAs do you support?
Just this one right now. And actually, this is from Xilinx. So we could fairly easily support other Xilinx FPGAs of this kind, but those are pretty low end. So as mentioned, we are working on higher-end FPGA support. Actually, that higher-end FPGA will be Microsoft's Catapult FPGA in the cloud, which is an Intel FPGA, by the way.
Cool. All right, thanks.
Well, thank you guys. Hope this was worth it.